Alright, so here we are with Chapter 5, Section 1. We're talking about perpendicular and angle bisectors. So, we're going to prove and apply theorems about perpendicular bisectors, and we're also going to apply theorems about angle bisectors. So, some of our vocabulary here is equidistant, that's going to happen, and then also locus. Alright, so in taking a look at Chapter 5, Section 1, when a point is the same distance from two or more objects, that point is said to be equidistant from those objects. So whatever it is that we have, if we have something in the middle that has a distance that is going to be the same as the next distance, this point is the equidistant point. Triangle congruence theorems can be used to prove theorems about equidistant points. So when we talk about our previous chapter of side, 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 angle, side, those are going to be helpful in understanding this equidistant idea. So, taking a look at two new theorems that we're going to be talking about. One of them is just the converse of the other, so it's really just one theorem. And our theorem is the perpendicular bisector theorem. So, our parameters are if a point is on a perpendicular bisector of a segment. So we've got our perpendicular bisector. And we are talking about a point on this line somewhere. Could be right there in the middle, could be anywhere along there. Then it's equidistant from the endpoints of the segment. So that means that these pieces are going to be the same length. It could also be these segments, but the idea is that if you have this perpendicular bisector, any point on that line, wherever it is, if you connect them to the endpoints of that segment, you're going to end up with two of the same lengths. And why does that work? We talked about it earlier. It's because you already know a side and a side from reflexive and an angle. And so by side, angle, side, we can say that that other side has to be forced to be congruent to the other one. So this side has to be, at this point, it forces it to be the same as this side. So again, by side, angle, side, we now have two congruent triangles, meaning their hypotenuse are the same. The converse is true, so let's say that you happen to know these hypotenuse first, and then you're going to go and say that these sides are congruent. It also then CPCTC comes into play afterwards. This one here is going to be by hypotenuse leg, so by HL and then by CPCTC, that segment can be the same and therefore it can be perpendicular. So, pretty interesting that our previous chapter is kind of encompassed in this idea. So, locus is a set of points that satisfies the given condition. So what I've been drawing here of a bunch of points that happen to be on this, if you continue to draw all the points that might exist on that line, that is a locus, the set of points. They like to talk about a locus as a circle as well, because a circle is made up of the set of points that are a given distance from a center. And so if you give the entire set of these points and you get every single one of them, it starts to make a solid line. So the perpendicular bisector of a segment can be defined as the locus points on a plane that are equidistant from the endpoints of the segment. So again, this line that I was drawing here are going to be the set of points that are equidistant from these two endpoints that we made. Alright, and just a little reminder, the distance between a point and a line is the length of the perpendicular segment. So they're going to meet at 90 degrees. So if I ever want to talk about the distance between two pieces, so a line, for instance, and a point out here, it does have to be that distance that meets at 90 degrees. And so that is going to be its distance. Technically, you could measure from here to here, but it wouldn't be called the distance anymore. It would just be called the length between two points. Alright, and so that's what's going to be used in this next one, because we're talking about the angle bisector theorem. So the previous one was the segment bisector, but now we're doing an angle. So an angle is being bisected. You can see as we have these two markings here saying that the two angles are the same measurement. If a point is on the bisector of an angle, so here's your bisector of the angle, and if there is a point on there, as we were talking about, any point on there, then it is equidistant from the sides of the angle. So this one actually comes from angle, angle, side, because we are given, of course, the angle that's bisected. We're given the side that makes up this locus. And then we're also given that, well, it has to be at 90 degrees, otherwise it's not a length. So we actually get, by angle, angle, side, that from CP/CTC we would be able to say that this length is going to be equal to that length. Very exciting. So the next, of course, is its converse. So instead of getting the two lines, we are now given those two segments are the same. And so because we're given the two segments are the same, then we can determine that those two angles are congruent. So this one is going to be based on, again, our angle that we have here, this side that is going to be reflexive, this piece that was matching to this piece here, and so officially our three-letter congruency is going to be by angle, side, side, so by HL. So it's a hypotenuse of a right triangle and a leg. And then, of course, after that, CP/CTC to then say that the two angles are the same because they were in the triangles together. All right. So, based on these theorems, an angle bisector can be defined as the locus of all points. So again, as I kind of drew in this previous one, these are the locus of all the points. This angle bisector is the locus of all the points that are equidistant from the sides that make up that angle. So we've got a little quiz here. It's going to use the same diagram twice, but the first one here tells us that we have ABD as 16 degrees. So ABD, so that's here. So if that is 16 degrees, they want us to find ABC. So how do we get to actually find that that's ABC? Well, most likely there's going to be some doubling going on here. And especially since we're talking about an angle and not a side length, we're actually going to be using this theorem. And hopefully you can see the setup is actually given almost the same image as this one here. So since it's almost that same image, that means that we're using the converse of the angle bisector theorem. And so because of that, that means that angle ABD is going to be congruent to angle DBC, and so therefore if that's 16, then this is 16. And so if we want the measure of angle ABC, we just need to do 16 plus 16, and so it's going to be 32 degrees. Again, the same diagram is going to be used in the next one, so I can't necessarily keep those images there. But they're telling me that ABD, so that top one, is going to be 2x plus 12. And then the next one is going to be 6x minus 18 as the angle. And so just as we had before, those two are, of course, equal. If it was 16, then the other one's 16. So we actually get to take 2x plus 12 and set it equal to 6x minus 18. And the reason that we can do that, again, is by the converse of angle bisectors theorem. If we have these two that are the same length at 90 degrees, that reflexive side, we have HL, and therefore we have two angles that are the same measure. So putting these together, let's see, I'm going to add 18 to both sides, get 2x plus 30, and then I'll subtract my x over, and get 30 equal to 4x. Divide by 4 and get an ugly x value just because it happens to have a decimal of 7.5. That's not what they want. They want you to find the measure of ABC. So in order to find the measure of ABC, we need to plug in this x value of 7.5. And so angle ABD is going to equal the sum of this, so 2 times 7.5 plus 12. And so if ABD is 27, then it turns out that the other one, which was CBD, is the same. And so if we add 27 and 27, we'll get 54 degrees, which is the measure of the entire angle ABC. Alright, this next one here uses the previous theorem, so the segment bisector theorem. And we're going to be given that FH is the perpendicular bisector, so we are given that this has been bisected. And so those two pieces are the same, and those are both 90-degree angles there. EF, so this hypotenuse here is going to be said as 4y minus 3. And then this side over here, FG, is going to be 6y minus 37. And as we can see by side angle side of this triangle, or by that perpendicular bisector theorem that we were talking about, let me get the perpendicular bisector theorem, we are going to be able to say that those are the same. So we know that EF equals FG, and so therefore algebraically we can set them equal to each other. So 4y minus 3 is going to be equal to 6y minus 37. So if we solve that, that means that I'd move maybe my y's over. And then my value number over. So we get 34 equals 2y, or if we divide by 2, we get 17 is our y value. Of course, that's not the answer because they want you to find FG, so we have to plug it back in. So we plug in a 17 right there. It's a really ugly 17. And so if we plug a 17 in back there, we're going to say that the length of FG equals 6 times 17 minus 37. Or 6 times 17 minus 37, 65. Alright, and then the other one says that we have an EF and an EH this time, and an FG of 10.6. So going back up to our diagram, they're telling us that EF is 10, EH is 4.3, and FG is 10.6. And so they want EG. And so because we know, oh, I missed a 0.6 here. And so because we know that these two sides are the same length, and therefore the reflexive property also works, and then this has to be 90 degrees for linear pairs, we can now say by the converse that we do have EH equal to HG. So EH equals HG by the converse of the perpendicular bisector theorem. And so because of that, if EH is 4.3, that means HG is also 4.3. And since the entirety of EG is EH plus HG, EG is just 4.3 plus 4.3 again, or 8.6. Alright, so those are our notes for 5.1, and so you're going to be using both of those theorems and this idea of a locus and equidistant in order to prove some theorems about angles and segment bisectors.